I will put here the HDMI. So we have a better resolution. Okay. Is that okay for you?
Yes.
Good on Zoom, just good for you.
Yeah. I think so.
All right. So good.
Okay, next we have Owen from KU Leuven. Yeah.
Okay. Yes, KU
Main Institute. So he's going to be talking about impact of a binary companion in AGB outflows in spectralized and working towards realistic wind driving. Thank you. I almost lost it. Okay. Yes, feel free to go.
Right. So hello everyone. I'm Owen. I'm a first-year PhD at the KU Leuven. And indeed, I will talk about two things. First of all, what I did so far with Phantom, which was studying the impact that a binary companion can have on the resulting spectral lines. And also what I aim to do in the future, which is improving the wind driving mechanisms that we currently use. So since I'm the first to talk about AGB stars, I'll also introduce them. So AGBs, or asymptotic giant branch stars, are the evolved versions of low to intermediate mass stars. So these have typical initial masses between 0.8 and 8 solar masses. Now, in this phase of evolution, which is really one of the final stages that these stars can go through, they strongly increase in size. Typically, their radius increases by at least a factor of 200. And so these stars also cool down whilst increasing their luminosity. And so on the HR diagram, they're typically located in the very upper right part. Now, these stars are also known to exhibit very strong dust-driven winds. And these can reach typical mass loss rates between 10 to the minus 7 and 10 to the minus 5 solar masses per year, with typical outflow velocities ranging between 5 and 30 kilometers per second. But how are these winds actually driven? This is nicely shown in this picture. So starting on the very left, we have the star itself. So it's still synthesizing elements, and it's also prone to strong convection and dredge-ups. And these stars also strongly pulsate. And these pulsations can shock material, essentially levitating this material up in the higher, cooler regions. And then this combination of a higher density in these cool regions is ideal for dust formation. And upon this dust, then the radiation can start to push. And as the dust is driven out, it will drag along the surrounding gas, leading to then a steady outflow of material. Now, for a very long time, these, the resulting outflows were believed to be spherically symmetric because there's no real reason to deviate from this, or so we thought. Because now with observations using, for example, ALMA, which are shown here on the right, we now see that a wide variety of complex structures can actually be found in these kinds of systems. So we see, for example, some spiral-like structures, some arcs, and even more complex behavior, and even bipolar outflows. These different morphologies is that there is a previously unrecognized binary companion hidden in this outflow, and as it is orbiting around this AGB star, it is shaping the wind. Now, the most important parameter when it comes to these systems is their mass loss rate. Because, well, first of all, the mass simply determines the further life of your star, but also the mass loss rate determines the amount of enrichment that the ISM experiences thanks to these systems. And so these this mass loss rate is often derived using the CO spectral lines that we observe from these systems. But in this modeling procedure, almost always the assumption of a spherically symmetric single star outflow has been used, which we now know is quite far from what is actually happening. And so the question then becomes, are we perhaps making a systematic error on the derived mass loss rates and also on the galactic evolution modes? And so to try and make a step towards answering this question, I aim to model these lines using then 3D hydro simulations where I include this complexity in modeling these lines. So for this, we then used Phantom. So there we have a setup of a mass-losing AGB star plus a stellar companion. And to be able to generate some different looking morphologies, I've used 3 values for the orbital separation. But for simplicity, I still remained at a circular orbit and also a constant lower mass loss rate with also always the same masses for the AGB star and its companion. Quite important to mention is that to actually drive this wind, we just use a free wind approach. So instead of these pulsations combined with dust and radiation pressure, we just inject particles that are located on spheres into our simulation at a certain initial outflow velocity, for which I've again taken 3 different values to generate different morphologies. So if we have a look back at what I showed earlier, we're essentially ignoring this entire part and just focusing on the outer outflow. Finally, I also only included H1 cooling. So this is needed for the very high temperatures that can be found in the shocks. but you will hear more about cooling on Friday. So now we can have a look at the simulations themselves. So here on the top, I always show the face-on view, in the bottom, the edge-on view. And this is for the initial outflow velocity of 10 kilometers per second, and each different column refers to a different orbital separation. So if I can pause this on a good time now. So clearly in the face-on view, we always have this very pronounced spiral structure, which is because, first of all, our AGB star is orbiting around the common center of mass, and then secondly, the companion is impacting the outflow as it is orbiting around this. So this is regardless of the orbital separation, we have a very pronounced spiral structure. In the edge-on view, we see some more variety. So for example, at the lowest separation, you see these arcs that have been flattened towards the orbital plane. So also our entire model has actually become a bit oblate. Which is not anymore the case at the higher separations, where we see these almost triangular looking arcs that reach significantly higher. Should also mention this is zoomed in quite significantly on the inner part. The entire models are significantly larger than this. To create the spectral lines, I've used Magritte. So Magritte is a 3D line radiative transfer code that is also developed at the KU Leuven. And it can easily cope with SPH models as input. It just needs a point cloud with newest neighbor information. And so we can represent essentially the mesh like this. And it's a full ray tracer. So for every point in this mesh, it will trace rays in all different directions and solve the radiative transfer equation along those rays, also assuming NLTE, so non-local thermodynamic equilibrium. So it has to do this iteratively until the radiation field has converged. You, of course, also need a CO density because we don't yet include chemistry in our models. So to do this, we start from a constant fractional abundance of CO with respect to H2. And then it's very important to also include photodissociation by external UV radiation, also including the complexities in our outflows. And so this is a way of then also determining the size that our models should have. Finally, because these radiative transfer equations can get quite computationally expensive to solve, Magritte also allows us to reduce this mesh. And so we always reduce by 75%. And so the new mesh we can also visualize, which looks something like this. So the morphology is still kept whilst the computation time significantly decreases. So we can have a look at our spectral lines, but first we'll have a look at what happens if you just use a single star simulation. So on the left, I have a single star simulation. There was nothing really that special to say about it, just a spherical outflow. And the corresponding spectral line is shown on the right. I'll see if I can get this away. So the corresponding spectral line is a simple flat top line profile. And this is also what we expect from the 1D models that have often been used in modeling these observations. At least this is expected in the optically thin case. If we move towards higher mass loss rates and you get more optically thick, you expect actually a parabolic line profile instead. So this we can strongly contrast with a binary star simulation. So here we have a face-on view where clearly the spectral line is neither parabolic nor flat-topped, but instead we see strong double peaks form in the line. So we can have a look at all the lines that I get from the small grid of models that I use. So on top, we always have the face-on view, on the bottom, the edge-on view, and this is always a 2-to-1 transition of CO. So there's a low excitation temperature, so this is essentially probing also the entire outflow. So we start with the models with a low initial outflow velocity, where we always see these double peaks form, regardless, again, of the orbital separation. They all look very similar. And the edge-on view, we have this strong central bump feature, again, regardless of the separation. Moving to intermediate initial outflow velocities, we again have these strong double peaks, but now we see some more variety regarding different separations. And we once again had a strong central bump. And so these lines so far all show that a binary companion can indeed strongly alter the line profiles. However, if we have a look at the dotted line here, this line is really approaching a parabolic line profile, which I previously mentioned could come from a 1D model. So this is also showing that the impact of a companion can go completely unnoticed if we just observe the spectral lines. Finally, for the higher initial velocities, we see some smaller peaks for this specific model and some smaller deviations from this flat top line profile. But if we look at these actual models, these are really approaching a flat top line profile that look very similar to the single star simulation. And you can imagine if we add on top of this noise, they become completely indistinguishable. Now, we can also have a look at higher CO transitions. So higher transitions have a higher excitation temperature, so they probe more in a region. And we immediately see that some more features actually become visible. So on top, I show the 2-to-1 line, in the bottom, the 6-to-5 line. And so, for example, in one case, we see that 2 peaks completely disappear. But more importantly, in the edge on U, which are really approaching these flat top line profiles, we now see that all the lines also exhibit features that are incompatible with this 1D model. For example, these strong double peaks for this one specific model. And so this is what I was doing so far. So we can kind of conclude that these simpler models with these free winds already show the importance of including binarity in modeling these spectral lines, and that they can also serve as indirect evidence for finding binary systems. So now I'd like to go a bit on what I aim to do in the future. So if we just ask ourselves, like, how accurate are our models if we compare them to actual observations, then we see on the left where I have the models, we always have this super pronounced perfect spiral structure. But this is not really what we observe. And instead, we have way more chaotic behavior. And you can barely even recognize a spiral structure to begin with. And I think the most important thing to work towards these more complex systems is to also include these pulsations. So this is what I aim to do in the near future. So the first way of trying to implement this is by using an oscillating inner boundary in some initial density. And this has actually already been implemented in another SPH code, namely Gadget, by ID and Mohamed. And so this I'll show you on the slide, but I think it's barely visible, but you see some shocks that are driven by this inner boundary. So this we would then combine with hopefully detailed dust formation and also radiation pressure, such that we are actually driving this wind in a physically realistic manner, instead of just injecting our particles at some velocity. This then also introduces additional complexity in our models. So these authors also ran a binary star simulation where we see, again, a spiral structure, but now we see also the shocks that have been formed by these pulsations. When this hopefully works, I would also like to go one step further, actually, and also include non-radial pulsations, because we know that actually these AGB stars also exhibit non-spherical mass loss rate. And if we include that, we get some complexity basically for free. Alternatively, there exist these very nice detailed 3D models of the interior of AGB stars. So these are the Freytag and Hofner models, which is made using the Cobalt code. And these authors, they get self-consistent convection and pulsations. And so here, the non-spherical mass loss rate comes out as well. So here I show a snapshot of one of their simulations, where clearly, these different bulbs are the mass loss rate. This is just a star. And so if we were able to somehow use this as an inner boundary or somehow mimic, this kind of structure to begin with, and then also combine this additionally with a binary companion, I hope that we can get very close to the complexity that we also see in the observations. And that is it. Thank you for listening.
Thanks, Owen. We have plenty of time for questions, but
I can wait for this. Thank you so much. I wanted to ask about the very efficient grid that you have for the
Sorry, can you repeat, because the noise was... Yeah.
Could you please tell me about the very efficient mesh you have? So, like, one of the things we have on the board is faster MC fast, and you guys have achieved some efficiency by you reduce your grid by 75%.
This thing.
Yeah. Can you elaborate on that?
How
does that work?
The way that this is done, so we start by just calculating the entire Voronoi mesh.
Yeah.
And then, I didn't make the algorithm, but you start with plotting it on a mesh, I believe, and then inside a box you define some maximum variation you want to have in a box, and as long as your variation is less than that, you replace the entire box by a single particle, and you keep doing that until you reach either your maximum recursion depth or your maximum variation that you assume, and then you make it again a point cloud.
very nice talk. And I have a question. So we expect like that around these stars, there are planetary systems. And I was wondering whether the possibility of a planetary system around one of these objects could explain the complexity you observe in the observation.
So we have also models with a planetary companion, with, well, some Jupiter masses. And we do still see some kind of spiral structure, but in general, the amount of impact that a planetary companion has compared to a stellar companion is way less. And I believe, especially when you go to spectral lines, it becomes completely unnoticeable.
Thanks.
We have a question online first, so you'll be after. So who's that person?
Youssef, yes, him if
yes.
ask his question.
Yeah, yes. Can you hear me?
Wait a sec. One
Thanks
second.
for the nice talk. The question was partially answered, but I would like to know, we know that binarity is present in AGB stars, and I'm curious to know how binarity can influence the mass loss rate.
Well, that is kind of the question that I aim to answer in the future. So I don't have the answer yet, because in the models currently, the mass loss rate is an input parameter, which is kind of an issue. Yeah. So I want to make the mass loss rate an output parameter instead, which I hope to accomplish by improving this wind driving mechanism.
Okay, thanks.
Okay. So in the setup, you have this binary, and you have a number?
In the beginning, so if we actually, there is nothing. So, well, this is even dump 1. So dump 0, you just have your 2 sync particles. So in the beginning, there is just vacuum, and you just like really inject the wind.
And you can see in the surrounding, or?
Can you repeat, sorry?
You have some material in the surrounding?
So in the beginning, there is just the 2 sync particles, really, which makes them really fast in the start, which is nice, but no.
Any other questions? No? Well,
I think if you speak loud enough, it's okay.
I mean, I was wondering, well, sort of discussion, how realistic is it to have a, when you sort of answer the question, how realistic is it to have a spherical pulsating boundary?
Well, as a first approximation, it's still better than what we do currently, which is just driving this wind. But I think it's if you especially look at these nice interior simulations, it's quite far from what's actually happening. So that's why I would like to try to include non-radial pulsations as well.
Have you guys talked as well?
A bit,
yeah.
But it's going to be a difficult problem, I think, to simulate this self-consistently. But maybe using these kind of simulations as an input.
Yes, that's what I meant with use as an input boundary.
Right?
Somehow.
So then one comment would be, so it's developed a module where you can kind of pump the output of one simulation into another one, which is sort of something you can do here.
But I mean, first need this model as well.
So what kind of pulsation is that? Which ones?
What kind of, sorry?
Of pulsations. So
I actually don't know because they don't put it in. It just comes out really out of the simulation.
Just from envelope convection.
Yeah.
But you cite some models, P models, F models, G models.
I think it's, well, mainly the fundamental mode, but.
So you can't think of these as, well, I don't think they're really P modes, but they're just the convective bubbles that unbind material.
Okay, so it's, okay. So it's distortion due to convection.
Yes.
Okay. Okay.
Go on. Well, not science. It's on schedule.
I can go on the scans. So is that related to astroseismology? Are you with Penny Earth?
No, but she's also at KU. Yes.
For astroseismology. Yeah, but if it's on astroseismology, I'm just want to ask, you're planning to couple it to laser or gyro?
It's not on my to-do list. I think.
I don't know, because it's usually with KU, it'll be gyro.
Yeah, but they also, at K11, they don't really do AGB pulsations,
Okay.
they do
Oh,
other stars.
So those are usually evolved.
Yeah, I think mainly do
Okay.
non-evolved.
Okay, all right. And any other science questions? If not, we know.